Hey everyone, Mr. Weissert here. Today we're going to be going over one of my favorite probability distributions, the binomial distribution. Let's get started. I'm going to have my camera off because there's so much information on the screen. I don't want my face covering it. Here we go. This lesson will be found in Module 2, Lesson 6, Binomial Random Variables. In the textbook, you can find it in Section 6.3, and in AP Classroom, you'll find it in Sections 4.10 and 4.11. Let's take a quiz. You've all taken quizzes before. I'm sure you've had multiple choice quizzes probably every year of your schooling. And today we're going to talk about taking a 5-question quiz. Very simple. You either get it right or wrong, and each question has 4 answer choices, so you have a 25% chance of getting it right. They're not related to each other. We want to ask a few questions. Are the outcomes binary? Are there 2 possible outcomes, success or failure, for each question? And the answer in this case is yes, right or wrong. What about independent? Does knowing the outcome of one question impact the other? They shouldn't, so those are independent. What about, is there a fixed number of questions in this case? Yes, we have 5 questions. And is the probability the same? Assuming that we have 4 answer choices for each, the probability for getting it correct will always be the same, 25%. So we have what's called a binomial random variable, binomial. In this case here, we want to check our bins. B for binary, I for independent, N for a fixed number, and S for the same probability of success. So let's answer a couple questions. First, what's the probability that X is 0? So X being the correct number of guesses. Well, in this case here, to get nothing, the probability of getting them all wrong would be something like 75% multiplied by itself 5 times. Since these are independent events, we use the multiplication rule. So 0.75 times 0.75 times 0.75 5 times, or you can do 0.75 to the 5th power, which is 0.2373. So look at the question, part B. What's the probability of getting them all correct? 5 correct guesses. So in this case here, you do 0.25 to the 5th power, or 0.25 times 0.25 times 0.25 5 times. You're going to get a very small number. Now, a little bit of warning about your calculator. It is going to put it in scientific notation. So when you're doing that, remember with scientific notation, to get it as a decimal, because you don't want to write it like this, you're going to move it, in this case, 4 places to the left, and you're going to fill in those places, those blanks with 0. So it's going to be 0.000976565. So the probability of getting them all right is very, very small, which you could imagine if you had guessed them all and got them all right, you'd be pretty lucky. Part C, what's the probability of getting at least 1 correct out of the 5? Now, we've done this before. This is the complement rule of getting none of the questions correct. So what we do is we find the probability of getting at least 1 by doing 1 minus the probability none are correct. We've already calculated the probability of none correct, which is 0.2373. So we can subtract that from 1, and we get about 76.27%. So we have a 76% chance of getting at least one of those questions correct. Part D, what's the probability of getting exactly one question correct? How many different ways are there to do this? This one's a little tricky. So if you think about it, you can get the first question correct. And if you just do it like that, 0.25 times 0.75 to the 4th power, you'll get a fairly small number. But you think there should probably be a higher percentage of getting exactly one question correct because you're going to have 5 questions. Getting exactly one correct out of many, many trials should be a higher probability. Well, if you think about it, there are more ways to do this probability. You can have the first one correct, you can have the second one correct, third, and so on. So really, there are how many ways to do this? 5. So the first correct, second correct, third, and so on. There are 5 different ways to do this. So we have to take that probability 0.0791 and multiply it by 5. And you're going to get a bigger number, 0.3955. What about part E? What is the probability of getting exactly 2 questions correct? Well, let's think about 3 or 4. That's going to be a little bit tricky because now we have multiple combinations of things. So we're going to do a simulation. This gets more complicated with larger numbers. So we definitely want to perform a simulation to see how we can estimate these probabilities. So the first thing you're going to want to do is set your calculator correctly. So we're going to go to our math menu. We're going to seed our calculator first. Then we're going to go to our math menu and go to prob. we're going to pick a random integer. Now we want to simulate a 25% probability. So I'm going to assign the numbers between 1 and 4 with having 4 being the correct answer. You could really choose any correct answer you want, but 4 is going to be my correct answer here. My lower bound is 1, my upper bound is 4. I'm going to select 5 questions to simulate a 5-question quiz, and we're going to count how many 4s we get. We're going to repeat this process several times. So let's break it down how it would look on the TI-84. First thing, you want to seed your calculator. So type in a bunch of random digits, go to your math, prob, rand, and press enter and get that calculator seated because chances are your memory's been cleared. Second thing, you're going to simulate that 25% by going into the random integer. Don't do random integer no repeats because we can get answer choice B, for example, multiple times. So we want to do random integer. We're going to select 5 random integers. We're going to count how many 4s we get each time. So in this case here, I've had 4 little trials, and I have 0 correct, 2 correct on the second one, 0 correct, and 0 correct. So we're going to do this a bunch of times and get ourselves a simulation. And I've done that for you. We have 100 simulated trials here. 0 correct answers, I got 23 times, so 23% of the time. 1, I got 38. I got 28 for 2. I got 10 for 3. I got 1 for 4 correct answers. I didn't get any for 5. So each dot is going to represent one simulated 5-question quiz. Here's the percent breakdown. Now we can put that into our probability distribution and look at the graph. So it'll look like this. Looks like it's going to be a little bit skewed to the right, peaked at 1, which is about what we expected. So now what we're going to do is figure out the correct way to do this theoretically without having to go through a simulation. So how many ways are there to get 2 questions correct out of 5? Well, let's think about the breakdown here. Okay, the probability of getting 2 correct theoretically would be 0.25 times 0.25, and then 0.75 times 0.75 times 0.75, multiply them all together. You could also use the exponent rule and just do 0.25 to the second power and 0.75 to the third power and multiply those together. But again, 2% is not quite matching our simulation of 28%. So what's going on with that? Getting 2 questions correct out of 5 can occur many ways. How many ways? Well, let's think about it. The first 2 could be correct. Maybe the first and third, first and fourth. Pause it, see if you can figure that out. All right, I'm going to reveal the answer. So it looks like if you count them all up, there should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different ways to do this. So we're going to have to multiply that 0.026 by 10, and now we'll get a number that's a little bit closer to our approximated simulation. So 0.26367. Now, how do we get that 10 without having to do all that? Because you don't want to list everything out. That's way too much. So we're going to do something called what is a binomial coefficient. It looks funky. It has a weird formula. It involves factorials. Let me break that down for you, what that looks like. So the binomial coefficient is basically a combination. So if you've taken a math that has used combination, it's going to be this little NCR. I'm going to show you in your calculator how to get that. So what you're going to do, if I wanted to show how can I choose 2 things out of 5, I'm going to go to my math menu. I'm going to go to prob, and I'm going to do the third option, NCR. That's a combination. So what that means is 5, choose 2. 5, put the bigger number on the left, smaller number on the right, press enter, and there's your 10. So we can actually do that with any sort of combinations. So there's 10 ways to choose 2 things out of 5. That's the binomial coefficient. So when you see it look like this, when you have this little thing going on here with this parentheses, that's not division, okay? That really is just 5, choose 2. So you're not going to see a fraction bar or anything like that. And I like to think of it as 5C2. Don't worry about having to use this formula. You just have to know how to get that in your calculator, and you won't have to show that work. So again, here's a little bit of a visual for you. Now what we can do is we can verify that 10 multiplied by 0.25 to the second power and 0.75 to the 3 power is going to be 26%, which is exactly what we calculated earlier. So now let's get this all with the right numbers. Now we know how to actually get that. So that first one, we're going to choose 0 out of 5. So 5, choose 0, 0.25 to the 0 power. Now anything to the 0 power is 1. And in fact, if you do 5, choose 0, you end up getting 1. So there's only one way to choose nothing out of 5, and that's all of them not being 5. So that's going to be 1 times 0.75 to the fifth power. So we've already calculated that. That's 0.2373. And similarly, we can do the same thing through all the other ones. So I'll kind of breeze through those. 5, choose 1, 0.25 to the first power. There's one less of the incorrect questions. So that's going to be down to 4. That's about 39.55%. 5, choose 2. We just did that one. 5, choose 3. Also has 10. So 10 is going to be your number up front. That's going to be about 8.79%. 5, choose 4, real tiny. Remember, I got 1 in my simulation, and this in case is about 1.46%. And even though I got no 5s, there is a probability of getting all of them correct. It's just really, really tiny, so it's 0.00098. So you can look at our simulated results and see that they're pretty close to them. So our simulation did a pretty good job in this instance. It's going to be skewed right still with a single peak at 1, because it's going to match pretty closely what our simulated results were. So now we can answer a few questions. If we were to take many, many 5-question multiple choice quizzes with 4 answer choices, what's the expected number of questions we would get on each correct on each quiz? Well, let's look at our stat menu. We can put it in L1 and L2. Go to our one variable stats, put frequency list for L2, and we can get our mean, which is the X bar, 1.25, and we can also get our standard deviation, which is 0.968. So we probably be expected to show a little bit of work on that mean, but that seems to come out a very suspiciously nice answer, and there's a reason for that, and we'll get to that a little bit later. But why? Think about why that might be so nice of a number. H, find and interpret the standard deviation. We're not going to do work on that. We'll look at that as 0.968. And so after many, many trials of these 5-question quizzes, we'd expect to be about 0.968 off from the mean typically. Part I, what's the probability of getting at most 3? Well, that would be less than or equal to 3. So we just add those 4 numbers together and you get about 0.9844. What's the probability of getting 3 or more? So that's going to be greater than or equal to 3. So we're going to add those 3 together. Should we be surprised if a student got 3 questions correct simply by guessing? Well, in this case, I would say no, because you got a 10.35% chance of getting at least 3 correct by guessing. So that's not unusually low. And remember, 5% is kind of our threshold. And just a reminder here, you know that in a probability distribution, all of your probabilities should add to 1. So you might want to take a minute and just double check that those 6 probabilities add to 1, but they do. And so we've done this correctly. So here's a little summary on the binomial distribution. You're going to be given these 3 formulas, the binomial distribution with the parameters, the number of trials, and the probability of success. You're also going to be given the mean and standard deviation formulas with those. Now, we actually have a formula that's a slightly different than what's in our probability distributions for random variables. So let's talk about that. So on your formula sheet, right below the discrete random variables, you're going to find the binomial formula, and it's got that funky nx over on the front side. That's your binomial coefficient, just ncx. 5, choose 2, 5, choose 3, whatever it is. Your mean is simply the number of set number of trials times the probability. So if you think about in our scenario, we had a 25% chance of guessing correctly, and there were 5 questions. So if you multiply those together, you should get 1.25. The standard deviation formula is slightly varied from the random variables. It's the square root, and it's going to be the NP times 1 minus P. Again, all that's going to be provided for you. So you just have to know where to look for it on your formula sheet. And it'll be right here in this table underneath the discrete random variables. So let's verify the means. Our mean formula was the number of trials times the probability of success. We got 5 times 0.25, 1.25, which is the same thing as what our calculator said. Our standard deviation, if you do the square root of 5 times 0.25, 1 minus P is 0.75. So if you multiply all those together in the square root, you'll get about 0.968, which is the same thing our one variable stats said. So everything checks out. Also, on your calculator, you have to know how to get the binomial quickly because some of these questions are going to be very geared toward using the calculator's functions to get the answer. So fortunately for us, we have a menu to get the binomial formula. So you're going to hit second vars, and you're going to go all the way down to where you see binom. Now there's two binomials. There's the binomial PDF and CDF. We're going to do PDF first. Let's say I wanted 5 trials, and I knew the probability of success was the same, 0.25, and I want to know what is the probability that I could get 3 of those 5 correct. So that'd be binomial PDF, and you're going to get 0.08789. Now you have to write all of your information when you're writing this work. You can't just put the answer. So make sure that what you see in this box here, I'm going to cover it up. What you see in this box is what you would write out. Binomial PDF, number of trials 5, probability is 0.25, x is equal to 3. If you do that, that'll count for your work. Now, what if I want to do less than or equal to 3? So if you look at this question here, what's the probability less than or equal to 3? Now, we could add these 4 up if we got them individually. However, we have a workaround. So if I want to do less than or equal to a number, I would do second vars. I would go down to binom CDF. C stands for cumulative. So again, I have my fixed number of trials, 5. 0.25 is my probability. Less than or equal to, what was the number? 3. So I'm going to put 3 in there. I'm going to go down to paste. And that'll actually, what it'll do is it'll add 3, 2, 1, and 0 together and give you that cumulative probability, which is 0.9843. And so you can see that does match up with what we have in the table. So C for cumulative, P for point. Now, the calculator will only go less than or equal to. So if you're asked to go above or greater than or equal to, what you have to do, in this case here, if I want to know the probability of x being greater than or equal to 2, what I'm going to have to do is I'm going to go to my complement rule and say, what's 1 or less? So 1 or 0 in this case. Now, I have them here. I added them to get 0.63. What you're going to do in your calculator is the following. Again, greater than or equal to 2. You're still going to use CDF, but CDF only counts down. So since greater than or equal to 2 is the complement of less than or equal to 1, we'll put 1 in the place of the x value. Press enter 2 times, and it'll calculate the probability of getting 1 correct and 0 correct, which is 0.632. That does match up what we have over here. So always subtract that now from 1 because we want to go above it in this case. So the probability of getting 2 or more is the complement of getting the probability of getting 1 or less. So that 0.367 is going to be your final answer here because we have to go back and answer the question, subtract it from 1 and do what's 2 or more. All right, so in these examples, you might want to pause the video and read through these. What we want to do is determine if it's a binomial situation, and if so, talk about what that probability distribution looks like. There is a typo on D, so we want to make sure we can fix that. So if you're looking at in my class, just fix that typo. It says, repeat the process 10 times, and we're going to say let T equal the number of aces you observe, not let T equal the number of cards you had to turn over. That's kind of a holdover from my last one here. So let's look at the first one. You play a game of whack-a-mole. From playing this game in the past, you know that you have an 80% probability of whacking the mole before it drops back into its hole. The moles pop up randomly, and your ability to whack any particular mole is not affected by whether or not you whacked the previous mole. There are 20 moles to be whacked during one round of the game. Let X equal the number of moles you are able to whack. So let's check our bins. Binary, independent, fixed number of trials, same probability. Is it binary? Well, you either hit or miss, so that checks. Is it independent? If you look closely, the moles pop up randomly, and your ability to whack any particular mole is not affected by whether or not you whack the previous mole. So they are independent. Is the number of trials fixed? Yes, we have 20 moles to be whacked. Is the probability going to be the same each time? Looks like it, 80% probability. So we have ourselves a binomial situation. And so we say it's a binomial random variable. X is the number of moles whacked. I'm just repeating that from above. And we say binomial, parentheses, n equals 20 and p equals zero point 0.8. So you want to list the set number of trials and the probability after you write the word binomial in this case. How about part B? You start with a well-shuffled deck of 52 playing cards. Imagine that you turn over the first 10 cards one at a time. Let A equal the number of aces you observe. Let's check our bins. Is it binary? Yes, you get an ace or no ace. Are we independent? Oh, we failed that. We turn over the first 10 cards. It didn't say anything about putting them back, turning them back over after we turn them over. So we have violated the independent rule. It's not binomial. We don't have to check the other ones. We violated a rule, we violated a rule. So we do not have ourselves a binomial situation here. Part C. Start with a well-shuffled deck of 52 playing cards. Imagine that you turn over the top card. Look at it, put the card back in the deck, and shuffle one more time. Repeat the process until you get an ace. Let W equal the number of cards you had to turn over. Let's check our bins. Is it binary? Yes. Is it independent? In this case, yes. We're sampling with replacement. We're going to put the card back in the deck and shuffle. Do we have a fixed number of trials? We repeat the process until you get an ace. That is not a fixed number. So that is not a binomial. Fails one of the conditions. Letter D, start with a well-shuffled deck of 52 playing cards. Imagine that you turn over the top card, look at it, put the card back in the deck, and shuffle again. Repeat the process 10 times. Is it binary? Yes. Independent? Yes, we're sampling with replacement. Is there a fixed number of trials? Hallelujah. We have 10 times. What's the probability? It's always going to be the same, 4 out of 52, because if we're replacing it, the probability will not change. So we have ourselves a binomial random variable t. T is the number of aces drawn. Binomial, n equals 10, p equals 4 over 52. Let's do a check your understanding. Try this one on your own. All right, I'm going to start it back in 3, 2, 1. Here we go. A fast food restaurant is running a draw a 3, get it free lunch promotion. After each customer orders, a touchscreen display shows the message, press here to win a free lunch. A computer program then simulates one card being drawn from a standard deck. If the chosen card is a 3, the customer's order is free. Otherwise, the customer must pay the bill. On the first day of the promotion, 250 customers place lunch orders. Part A, what's the expected number of customers that would win a free lunch with this promotion? Well, in this case, we have 52 cards in a deck, 4 of which are 3, so our probability is going to be 4 out of 52. It's a binomial situation. We have a set number of trials, 250 customers. So the expected is just the number times the probability. That'll get you about 19.23. So we expect about 19.23 customers to win this lunch promotion. Not bad. Find the probability, part B, that at least 25 of the 250 customers win a free lunch. Now, this is a situation where you do not want to do this by hand. At least 25 of the 250, that's a lot of number crunching. So we're going to use our calculator. At least 25 is greater than or equal to 25. Remember, our calculator for CDF only goes below, at or below. So we want to subtract the probability of getting less than or equal to 24 from 1. Let's use our calculator's binomial CDF to get that answer. Okay, so again, we're going to do second vars. We're going to go down to binom CDF, that's a cumulative. Remember, our trials is 250. Our probability is, what's it? Aces, 4 out of 52. 4 divided by 52. Our X value, we want to know less than or equal to 24. So remember, whatever you put in there, it's going to count that as well as what's below it. So less than or equal to 24, not 25. So you get about 89.17%, but we have to subtract that from 1. So it's about 10.83%. Here's the calculator screen grabs. Actually, no screen grabs. That's why I did it for you. So subtract that from 1, you get 10.83%. Part C, find the probability that fewer than 10 of the 250 customers win a free lunch. Again, this is another CDF, fewer than 10. So that's really going to be 9 or less. So we want to think about that as less than or equal to 9. Again, use your CDF. And if I plug that into the calculator with binomial CDF, I'm going to get 0.006128. That's pretty darn small. So that's your math. It should be very small, about 0.61%. Less than or equal to 9 is the same as fewer than 10, less than 10. So part D. In fact, only 9 customers won a free lunch. Huh, that's suspicious. Does this result give convincing evidence that the computer program is flawed? Explain your reasoning. I would say so, because there is only a 0.6% probability that fewer than 10 customers would win a free lunch if the program's working properly, which seems to be very unlikely to happen by random chance alone. So because 9 won a free lunch, we, in this case, have convincing evidence that the program indeed is flawed, less than 5%. Part E just wants you to plot this on Stapplet and describe its shape. I added this part just so I could show you on Stapplet how you can get this value pretty easily. You would not want to use your TI-84 to get a histogram of this stuff. So watch how I do it. So you're going to go to stapplet.com, and under probability, you'll see binomial distributions. Click on that. Now, what you're going to do is you're going to put the fixed number of trials, 250 in this case. Now, the only downside is you cannot do 4 divided by 52 here. So you have to get the decimal for that. So 4 divided by 52 is 0.076923, blah, blah, blah. So I'll put 0.07692. That's probably good enough. We'll plot our distribution, and we'll see a very, very tiny sliver of different histogram widths here. And if you look at the very top peak, I know it's kind of hard to see, maybe I can zoom in on that. That top peak is centered around 19, which if you remember, our expected number was about 19 point something. So that should be your most common one. And it'll even give you your mean and standard deviation. And while we're over here, I can calculate different probabilities. This one actually does more than binomial CDF does, because I can go exactly a number. So if I want to know what's the probability of getting exactly 10, I could say 10. It's going to give me that percent. If I want to know less than or at most, less than would be like less than 10. If I wanted to know probability of at most, then that would be less than or equal to 10. And so forth. You can do at least, which is greater than or equal to. You can do more than, which is greater than. So you can actually even do betweens, although we won't ever really need that here. So we can do different calculations on our Stapplet that our TI-84 can't do, but it'll give you the mean and standard deviation here, and that should check out what we got earlier. So there. So let's look at what the question's asking. Plot this distribution on Stapplet and describe its shape. Well, they just want to know what kind of shape it is. Now, I would look at that and say, it looks like it's fairly symmetric. Let me get rid of this here. Oops, I forgot the number. Sorry, guys, you saw me get a little delay here. Anyway, that's going to be fairly symmetric. Looks like it's peaked around 19, so you can simply say um, approximately symmetric, centered at 19 wins in this case here. And there's all the information from the Stapplet website if you want to screenshot that. All right, guys, that concludes this video. The next video is going to be talking about how to approximate a binomial with things that aren't necessarily independent, but I wanted to split that up into a separate video, so this one did not go too long. So let's do a little summary. Remember to check your bins for a binomial. Binary, independent, number of trials fixed, same probability. This is the formula you're working with here. Again, you can use binomial PDF and CDF if you write the correct parameters. The mean formula you'll have to be able to calculate. So it's the number of trials times the probability. We say after many, many trials, we expect the average number of successful outcomes to be at least, or to be about whatever this is. Always write it in context. Standard deviation, square root of the mean times the complement of the probability. And you'd say the number of successful outcomes typically varies by about this many units from the mean in context. Again, describe the shape. We make a histogram of the probability distribution. It can be roughly symmetric. It can be skewed right. Just depends on where that percentage lies. Let me actually model that for you real quick. So let's just give you some numbers here. Throw some numbers in Stapplet. If I have a 50% probability, it's going to be symmetric. because 50% is right in the middle. So that bump's going to be right in the middle. So if I have 20 trials, then we would expect it to be peaked at 10 because half of 20 is 10. But let's say that is uh, maybe an 80% probability. Well, now we have what's going to look like a skewed left distribution because most of your peaks over here on the right, and it's trailing off in this direction. Now, if this were like less, let's say it was like 10, then that skewness is a little bit more pronounced. Okay, and the bigger that number is, the less it looks skewed because it seems like it's centering around that number in the middle. So I'll stick to 20 here to make it a little bit more like what we're used to. And if I go even closer to 100%, that skewness is going to be more pronounced. So that'll be skewed left. Now, if I go to the other side, so if I say 10% instead of 90%, then it's going to be skewed to the right and so on. So the skewness is really dependent on what that probability is and what the number of fixed trials is. Finally, we can calculate using the binomial PDF or CDF. Remember, C stands for cumulative, so only do it if you're doing at or below. And if the question calls for above or more, greater than or equal to, then make sure you're subtracting from 1. That concludes this video. Thank you for watching.